All right, so in this section, we're blending two sections together. 5.3 is similarity, and we really are only going to use the definition of similarity to help us talk about 5.4, which is diagonalization. And so diagonalization is actually a new, for us, factorization method. All right, so just like LU factorization was a way to factor a matrix, this is another method called diagonalization. But first, let's start with similarity. So we are going to get a definition of what it means for matrices to be similar. So we say n by n matrices A and B are similar. If we can write A equals P, B, P inverse for some invertible P. All right, so let's note here, both A and B have to be square matrices to be categorized as similar. And so if these two are similar, we can write them in terms of the other, P, B, P inverse. All right, so why do we care about similarity? Well, similarity is an eigenvalue relation. Okay. And so we're actually interested in matrices being similar to a diagonal matrix. So I'll write that down. We are interested in a matrix A being similar to a diagonal matrix. And you'll see how this is related to eigenvalues and eigenvectors in the next section. All right, so let's look at an example of a diagonal matrix and talk about properties that make them so helpful in relation to eigenvalues. All right, so let's say we have a diagonal matrix, D for diagonal. It's a 2 by 2 down the columns. I have 2, 0, 0, negative 1. All right, so a matrix is diagonal if it only has numbers in diagonal and zeros everywhere else. All right, what if we wanted to square this diagonal matrix? All right, squaring something just means multiplying by itself. So I'm going to write this matrix twice. And as we know, matrix multiplication can be pretty tedious, but nice things happen when we have a diagonal matrix. The result we get is actually going to be 2 squared, 0, 0, negative 1 squared, which is very convenient. And actually, we can generalize this for any power. So if we did d to the k, and this is our D diagonal matrix. This is only a property of diagonal matrices. We'll get 2 to the k, 0, 0, and negative 1 to the k. Very convenient. All right, so let's get our definition of diagonalizable. A, so our matrix A, is diagonalizable, very long word, if A is similar to a diagonal matrix. Let's call it D. All right, so remember, what does it mean to be similar? That means we can write A as P, D, P inverse for some invertible P. All right, so we can learn some things about A just because we're using the definition or the word similar. So A is similar to a diagonal matrix means that A must be a square matrix. So we're only talking about square matrices when we talk about diagonalizability. All right, so let's look at an example. So let's say that A is similar to a diagonal matrix, where A is a 2 by 2. So down the columns, I have 5, 6, -3, -4. P down the columns is 1, 1, 1, 2. And D, we're going to use our same diagonal matrix, 2, 0, 0, -1. All right, so A is diagonalizable. It's similar to this diagonal matrix D. What if I wanted to figure out what A cubed was? It may take a little bit of effort to multiply A by itself 3 times. But what we do know is that A is diagonalizable, so A cubed is the same as P D P inverse cubed. Which seems, maybe it's more complicated, but let's actually expand that out. So cubing something means multiplying it by itself 3 times. So I'm just going to write this 3 times. P D P inverse, P D P inverse, and P D P inverse. All right, so when we expand this all out, we should see some nice things happening, some maybe ways to simplify. Notice that the P inverse and the P are next to each other. That's the identity. So really, we have P D identity, D identity, D P inverse. But we know anything times the identity is just itself, so it's as if those aren't there. So P, D, 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 P inverse. Now remember, we have these nice properties of diagonal matrices, especially when we're raising them to a power. So P D cubed P inverse. So we see that if A is diagonalizable and we raise it to a certain power, we can just use the factorization and raise the diagonal matrix to that power, which we know we can do so easily because of this property of diagonal matrices. All right, so let's write a statement so we can have a generalization of what's happening. So in general, if A equals PD P inverse, so if A is diagonalizable, then A raised to the K is P D to the K P inverse. All right, and so this is something we can just use now as a property. All right, so we're going to actually work through this example with the numbers here and find A cubed using this in the next video.